is Christopher Bauer. Today, I'm pleased to present you my recent work, Penalized Bootstrapping for Reinforcement Learning and Robot Control. So now, where's the motivation of our work coming from, actually? Well, imagine the current situation. You have a robot sitting right in front of a wall, and the goal is actually to find the red cone you see here right behind the wall. He actually knows that the cone is behind the wall, and the current choice he has to take is rather to go left or to go right. And based on the current situation, he basically can't decide it. He randomly has to choose. And now, before going deeper into the motivation, I want to give a little recap on reinforcement learning for everyone that is not really deep into the topic. So, sorry. In every reinforcement learning setup, we have an agent. So in our case, that's the robot you've just seen. And an environment that, in our case, again, is the wall and the target and everything that surrounds the robot. And from the environment, the agent receives a state so that he knows where he currently is and what he sees and what his target is. For example, that can be an image, that can be the distance to go, or anything like that. And based on the state, he decides what to do. So he passes in actions to the environment and interacts with the environment. And then receives a new state. For example, if he decides to turn left, the camera view or his state will change. And based on the new state, he receives a reward. That can be anything. For example, if he actually crashes the wall, for example, when he goes forward, he just crashes into the wall, he gets a penalty, or when he actually finds the goal, he will get a big bonus. And then he can just play multiple interactions with the environment and collect episodes. And based on the experience, he can optimize himself to actually increase the gained reward during the interaction with the environment. So with that knowledge, let's go back to the motivation. Well, you know the image on the left, so he has to decide whether to go left and to go right. And we were at the point that he can't decide whether to go left or right. So at the point when he starts to explore the environment, he'll find out that on the left side actually is another wall. So the best choice is to go right. So what the key here is that exploration really helps, especially in the early stage of the training, to improve the final policy that the robot will learn. What are the problems here? Well, you can't actually visit all states. It's just computationally too expensive. So we need an exploration policy that's that advanced, that leads us to key states that help us understand the environment, but not to every single other one. And before coming to the actual part of exploration, what is the key in our work, I want to introduce you to the baseline algorithm we use to optimize the agent itself. It's called twin delayed DDPG, or short TD3, and it's actually based on deep deterministic policy gradient. And that method, again, splitting up into an actor and a critic. What does the actor do? Well, it actually is our policy. So it receives the current state and maps the state into some action he thinks is optimal in that case. And as the name says, it's deterministic. So it actually returns the concrete action signals. Well, on the other hand, the critic evaluates the actor. So it estimates the Q function, which is nothing else than basically an estimation on how well the actor does if he applies that action. And yeah, we can use that estimation of the critic to actually optimize the actor. So we go in the direction to maximize the estimation of the critic. And that whole setup, or the DDPG algorithm, is off policy. You don't really have to understand what off policy is, but it gives us the benefit to just use old samples. So we can start to collect from the very beginning of samples within a replay buffer and use those samples along the whole training and do not have to really just rely on fresh information, which is really beneficial. So now let's get to the point what makes TD3 different to DDPG, and that's actually just that they use two critics. Why do they do that? Well, as you noticed, the critic is quite important for the actual training on the optimization of the actor. So stabilizing the critic training, or the optimization of the critic, actually heavily stabilizes the complete training. So have that in mind, that the difference is basically just that they use two critics. But at the end, for the evaluation of the actor, you can just use either of those. It doesn't matter which one you actually take. Now, let's come to the exploration, which is quite often just used. Quite naively, they just apply epsilon greedy, which is you take the optimal action you've just computed with your actor and add some noise. And you basically then just explore around the optimal path, which is just quite naively. And therefore, you can't deeply explore new situations or new states. So how, as we apply neural networks, how does the network look like? It's for the critic itself, we have the state and the action as input, and then just have two dense layers. So it's quite simple. And that's what actually we desire, just keep it simple so it trains fast. And the final layer just returns the approximated Q value, so an estimation on how well the actor actually does. And the actor itself is basically the same structure. We just pass in the state and have a new network that, again, has two layers. And the final layer, or the dimension of the final layer, actually depends on the dimension of the action. So for the example of the robot you've just seen in our motivation, we just have a translational action, so how you should rotate and how fast you should go forward. So we have two dimensions. But that will change for the environments you will see later on. And as we try to modify the exploration here, we have to somehow modify the information flow of the algorithm. So for now, I will just visualize the baseline that will help you to understand what we have changed. So again, we have the actor that receives the states and maps the state into an optimal action, or the action he thinks is optimal at that point. And we join those two and pass them to the tuple of critics. And just take one of those, and one of those critics will return you the approximated Q value. Okay, so now let's get to the state of the art of bootstrapping. What is bootstrapping in that context? Well, it is that you have a distribution that you don't know, but you're really interested in the distribution, and you just replace that distribution with a number of samples you think that are drawn from the distribution. So what does it mean in our case? Well, we have a network, and we can imagine there's a distribution that is telling us how likely, yes? Okay, I will just keep going. If you have questions, ask. Okay, so there are the network weights, and you can imagine there's a distribution that is telling us how likely is a set of current network weights given the data set. In our case, it's just the past experience we collected from the environment. And now we are replacing that distribution, as we don't really know it, or not at least in the case of reinforcement learning, and replace it with a number of samples from the distribution, which means we're just multiplying the network itself. That is basically the key idea of bootstrapping here. So what is different in the state of the art? Well, they use DDPG and not TD3, so they have a single actor that keep in mind here. And they basically just multiply the actor-critic tuples. So again, for the information flow now, you have the state passed to each of the actors, and each of the actors returns you one action. And now they are paired, so you have multiple state action pairs, and they are passed to each of the critics. So the computational time here is in the squared order of magnitude, increasing with the number of actors you have, or actor-critic pairs. And now the critics decide which of the actions are optimal. So you always act greedy. And the current state of the art actually does apply that during training and evaluation. So they always act optimal and greedy. Yeah. Now, what do we change in our approach? Well, as is noticed, it does not change a lot in the structure itself. As we use T3 right now, we can actually keep the critic itself fixed, because we already know it's quite stable. We do not actually bootstrap the critic. So we just bootstrap the actor structure, as you can see here. And we introduced the number of actors is a hyperparameter. So if you decide up front how many samples of the networks, or how many networks we can train in parallel. So again, the information flow here now is you pass state to the actors, and each of the actor returns an action, and the pairs are passed to one of the critics. So you're not anymore in the order of magnitude of the squared, just scaled with the number of actors linearly. And then we have an optimal action in evaluation. So we're not doing that for training, we're just doing that at the end for evaluation, or if you apply our new train policy. So right now I have to tell you, unfortunately, with just that setup, we've not added any deep exploration so far, but I will come to that point later on. First of all, I again want to show you slightly what network structure or how the network structure changed. Well, the critic, we didn't change it compared to TU3, so it stays unchanged, but the actor actually does change. So we have a state that is passed to the first layer, which again stays unchanged, but we share that layer among all the actor heads. That the head refers to the network that basically takes the pre-encoded state and is just based on that state computes an action. So that's why they called head, and the first layer is a shared layer. Why are we doing that? Well, you can imagine that the first shared layer can be replaced with anything. For example, if your state itself is an image, you can't just have one layer of dense nodes. So you have to replace it with a bigger CNN network that actually encodes the whole image into a denser state that the actors can use later on. And during training, you don't want to actually multiply the whole CNN network because it's just too huge to train. So especially if you have, I don't know, a number of 10 or 20 actors. So we keep the first layer shared and then have actor heads now that again have the same in total sized network as before. So now I want to get a little bit deeper into the exploration or how we add exploration. Well, we do that by take a different approach for selecting the action. And actually we apply here Thompson sampling. And Thompson sampling basically just tells us that in a new state, you can't tell up front which of the actors will perform better. So what we actually do here, you can see that on the right here, we have the state that is passed to the group of actors, but up front we take some random index. So we choose a random actor and just act according to that actor, ignoring all the others. And we're not doing that for just one interaction. We do that for the whole episode. So when does an episode end? Well, you start in some initial state. And now let's go in mind back to the example from the beginning, from the motivation. The episode ends when either you crash a wall or find the goal or just spin for a certain number of iterations. So you just end at the maximum number of time steps. So yeah, that actually does not only add deepen exploration, but also saves us a lot of time, because taking the optimal action, we would have to evaluate each of the actors and afterwards take the critic and take the best action. So we're not only adding exploration, but also are faster than just being optimal. So now maybe some of you think of, okay, well, but if the actors do actually agree in the early stage of training because they all see the same data set, we can't benefit from it, and that's actually true. So what usually has been done is that that you mask your data set while you're collecting it. So each of the samples you've just collected, you pass also a mask that is randomly drawn or binary array that actually tells you if that specific sample belongs to an actor or not. So when you optimize your network and receive a sample that you should optimize your network on, you compute an optimization step and then look into the mask, and if your actor does not is not allowed to profit from that sample, you will not use that optimization step. And the likelihood that vector or that binary vector is drawn is again a hyperparameter that you have to tune up front. But as we noticed, that did stabilize the training, but we want to go a little bit farther and added a supportive penalty. So here we again want to prevent that diversity collapse, so that each of the actors, or that we can keep the diversity of the actors, especially in the early stage of training. So what did we do? Well, we used the potential field penalty. You might know that term from the field of electromagnetics, and apply that to the actions itself. So we have the difference in actions on a certain state, and actually penalize the inverted square distance. So you see the curve here, as the difference in action shrinks, the penalty increases. But as that would increase to infinity, which we can't allow during the optimization step, we just limit it at some point to ensure it's not going to increase to infinity. And especially at the very end of the training, we are still allowed to converge to some common optimal action. So what does that actually do? Well, it encourages a uniform distribution of actions within the action space. And that is somehow similar to the entropy cost you maybe have known from TRPO or PPO. However, as entropy can only be computed for a distribution, So you need a distribution over the action given your state, which we don't have as we're using deterministic policy gradients. So we basically mimic the behavior of the entropy cost, which is already known to quite stabilize the training, by having our bootstrapped actors that are deterministic and then forcing them to be uniform in the action space. And again, the limit we introduced and the scale that's called beta are both hyperparameters that have to be tuned up front. So now let's get to the experiments. Both the environments you see on the right will be used in the presentation, but for now, they're both robot-controlled tasks. So you have some robot, and you want to teach him to, in that case, walk far. So you receive as a state the joint angles. So each of the legs has multiple joints, and you receive the angles of those joints. And your actions are the torques you want to apply to those joints. And at the end, the reward is calculated based on the travel distance with some number of time steps, while actually penalize the amount of torque. So you want to have an agent that uses less torque and travels as far as possible. So you want to teach him to walk as efficiently as possible. And now the topper environment is called AND. It's, as you can see, a 4-legged robot. And on the bottom here, that is called Walker, and it's just a bipedal robot. So let's get to the general performance of our approach. Well, here you see on the x-axis the iterations. So that is each of the lines show one course of training, and at certain numbers of iterations, we just took the current policy and evaluated over a number of episodes and averaged the gained reward here you see on the y-axis. So that gives you a hint about the general performance of the current agent. And you see here, the red line is TD3, so that's our baseline, while the blue line is DDPG, which is the baseline of the current state of the art. And for both the current state of the art and our baseline, we actually outperform both in the environment called AND. And that is due to the exploration of the increased exploration. And not only that, due to our changed information flow, we are actually in training 3 times faster than the current state of the art regarding bootstrapping, and even 4 times faster in evaluation. So now you maybe have noticed that the orange line does not even beat his baseline, and I want to come to that right now. Well, what we assumed differently is that we say, okay, you have your baseline maybe already tuned for your current environment, and you don't want to retune all your hyperparameters. So you can apply our bootstrapping approach without retuning the baseline parameters and just tune like the number of heads and the mass probability for your data set, and in our case, beta, so your penalty cost. And actually the state of the art assumed that you retuned all the parameters. And here you see an environment where exploration itself does not really is beneficial, that you can't tell up front how beneficial is deepened exploration. So, but we can say that our approach does not really require a lot of retuning and only adds roughly 60% of overhead, and you get at least the performance you receive from the baseline, but usually can expect, of course, an increase in performance. So now I want to give you a little insight into the bootstrapping itself, and especially the number n, so how many networks you use. Well, all of our numbers actually do beat the current state of the art. However, you see here some saturating effect. So while the red and the purple line are still above the blue line, which is the lowest number of actors, from the red to the purple line, there's not much of difference. So you can't increase your number of actors to just infinity and say, I don't care about computational cost and expect an infinite reward. That's not going to work. And now at last, I want to show you how our penalty actually supports the whole training. A little reminder here, beta is the scale for the inverted square distance of the actions. And now we've not anymore showing you the whole course of training. We just took the final policy we received, so that's completely trained, and then averaged over some episodes the expected reward. And you see here a clear trend. So slightly increasing or just having a small beta usually stabilizes the training, and helps to converge. While, of course, if you just increase beta too much, so just to a super huge number, you force the actions to spread uniformly in the action space. And that can't be optimal because they can't agree on any given state. So there is an optimal, but usually what we've seen that if you take a reasonably small beta, so in that case, usually we start with 10 to the power of -6, you never get a harmful effect, and usually it really stabilizes the training. So now I would like to conclude everything. So using our bootstrapping approach, we were capable of improving exploration and therefore improve the performance. And compared to the current state-of-the-art bootstrapping approach, we are not only fast in training, but also in evaluation. And during our work, we focused on actually having our approach be applicable to any already tuned reinforcement learning setup that is deterministic. So you can just add hours without have to retune all the hyperparameters. And for future work, we are actually planning to apply that to robot navigation in cluttered environments, because we expect there that a lot of exploration is needed to have a beneficial, high-quality policy. So we want to work on that and see how great the fact is. And at that point, I would like to thank you, and you're welcome to ask questions if you like.
Yeah, thank you, Christopher, for your presentation. It was really nice.
Thank you.
Yeah, and I would now like to ask the forum if they have any questions to you. So, my question, Christopher,
Yeah.
you have used masking for the data set, right? The data
Yes.
set that you have used. So, what do you think, like, how does this have effect in final reward, you know, like when you're calculating the reward,
Yes.
what effect does it have, this masking?
Yeah, it does actually. You help to basically spread the actors. So you ensure that the actors do not agree on early stage on some state for the optimal action. So if you have a certain state, each of the actors should have a different idea what is optimal in that state. So you actually can benefit from Thompson sampling. So having, yeah, I would say new or possibly really good ideas in an already known state that are better than the current to be thought optimal action. So to be able to benefit from that, you have to ensure a difference in actors. And there the mass dataset really helps, because each of the actors do not have seen the identical dataset, basically.